Thanks, Stratos, and thanks very much for having me here and being able to talk to you. And please made it kind of informal. So if you have any questions at any point, just input up. I think I use this one, right?
Yeah.
And okay. So my main topic today is talk about industrial heat and what might be challenges to power industrial heat and also opportunities, right? So I'm a metallurgist by training. So in the end of the day, that's the only thing I really know anything about, just blacksmithing. Everything else is stuff that I kind of talk about, but there are other smarter people than me that work on it. Industrial heat. So I want to start out just by laying out the problem. And, industry in the US represents about 30% of all the industrial and all the energy use. Okay. And you can see that the majority of that is just by five sectors: cement and lime, food production, iron and steel, chemicals, and of course, refining, right? And that's kind of our focus, looking at these energy intensive industries. So out of that 30%, it turns out, and I won't go through the slide and all the details, but about half of all of that is just used for heating things. Okay, whether you're trying to smelt iron and steel, or whether you're trying to bake bread, it's just used for heating and reaching the process temperature, about half of all of that 30%. And that's kind of the focus of our institute, right? People sometimes think, okay, is it very narrow? But well, it might be narrow, but it's actually a pretty big chunk of the all the energy use that we address. Okay, so anything where you're heating stuff up. This is just a basically a Sankey diagram that shows the comparison between where industrial process heat is using. So what I said previously is just breaking it down into various areas. And some of it, you can also include refrigeration or cooling as part of heating, or temperature change as well, thermal transformers, as I see it. Now, the reason that this is important is for energy intensive industries, the energy efficiency is a big part of their operating costs, right? So the more energy efficient you can be, the more it adds value to your economics. So this is our economic case that we make, that for energy intensive industries, it's very important to maintain your energy efficiency and be as flexible or low as possible in your energy costs. And this is just a comparison between US, Germany, and Japan. We do believe that US has a unique position in all the abundant energy sources that we have, and how to optimize them the best possible way possible in terms of powering your industries. As part of this, we also are looking at the training of people that goes into these industries. So overall, there's a challenge in terms of manufacturing, that people are not going into manufacturing. And every manufacturing job is a multiplier. But for us, it's also an interesting problem, because as you'll see, process heating, especially through electrified process heating, it requires more knowledge of electric power systems and power electronics and electrical engineers into the manufacturing industry, which is mainly dominated, by chemical engineers or material scientists. So it's unique skill sets needed by those manufacturers as well. So why are we doing this? What might be the opportunities and what might be the challenges? I've kind of talked to you a little bit about the opportunities, but the challenges are such that whatever we do has to be economically viable. There has to be an economic case. We're not doing it for any other case than that. The bottom line of the industry has to make sense. And this is challenging, because in the end of the day, whatever technologies we try and support, they have to roll up to some type of a techno-economic model, right? And there has to be a payback, whether that's 5 years or 10 years or whatever that is. And that's difficult to do because a lot of things are dynamically changing as things go on. For example, we're getting more and more different types of energy sources into the grid. In Texas, I think you have a lot of wind power. In Arizona, we have potential for solar at scale. The government is promoting nuclear and hydro and geothermal. All that is getting into the mix. They all operate in different conditions. So that's changing our grid mixture as well. We also have different types of grids themselves being developed, islands, microgrids, national grids, all those systems, behind the lines. So all those systems are changing as well, developing different opportunities. For industry, there's also the challenge that there's competition for power. If you're electrifying industry, then there's other sectors that may have preference over this. Of course, residential needs for power, transportation. And most recently, in the last year or so, it's been the development of data centers. The advancement of data centers, it's much easier to put up a data center in terms of regulation than a manufacturing plant. And, it's easier to get permits for that. And that's almost, I guess, increasing the risk for industrial electrification. They're kind of almost moving away from it, right? So what might be the opportunities there? On the other hand, there might be ways in terms of co-funding. If you're looking at islanded systems and things like that, there might be ways of synergism that one can build around data centers. And then there's, of course, the economic models, right? There's electricity trading going on, and whether we accept it or not, there are carbon markets, right? For example, in Europe, you have the carbon emission rates that are giving you C-band, right? And also, even in US, you have the Foreign Pollution Act that's actually co-sponsored by Lindsey Graham and somebody from the Democratic side, but it's not passed yet, but it looks at basically a fee for emissions. So the cleaner you are, you would have an advantage in that. So those type of economic models have to be accounted for as well. So we need to adapt to all of these things as they change, and it's going to change the viability of technologies as things go on. So basically, what we are looking at is how can you power manufacturing using all the various sources of energy and be as efficient as you can, right? So if you look at the current government's priorities, it's hydroelectric, geothermal, nuclear, and also hybrid heating technologies. So if you're looking at something that might be conventionally heated with combustion, can you precision heat certain parts with other ways and make the product better, or maybe produce use more flexibility in terms of raw materials? So those are types of opportunities that we are thinking about. So what we are is a public-private partnerships, and our name that recently changed is called Electrified Processor for Industrial Excellence. When we first developed this institute, Mark and Stratos were part of it, and we developed this acronym. So we've tried to keep the acronym but change the name so that it reflects the priorities of the government, right? So we are the DOE's 7th Manufacturing Innovation Institute, and it used to be called Clean Energy Manufacturing Institutes, but the DOE is now forbid us from using the word clean, so it's manufacturing institutes. And what we are is a public-private partnership. So we have over 150 companies, and you'll see why we include the entire supply chain. So utilities, manufacturers, technology providers, etc. We have a federal budget of about $70 million over 5 years. Let's see if those 5 years last or not. And we have about an equal amount of industrial cost sharing or state cost sharing, to do what we want. So the priority areas of kind of what we are looking at is shown in this slide. And we started out focusing on scope 1, like what can you do within a factory to electrify process heat? What might be the opportunities there? How do you integrate process heat, electric heating technologies into manufacturing processes, right? There is challenges there, and I'll show you some of those challenges and opportunities as well. It's often not a one-to-one placement. But actually, a lot of our stakeholders, or some of our stakeholders, pointed out that, that's not the problem. Like, we do have electric heating technologies. We would do it if you just provided us that power. We doubt that you're going to be able to give us that power. And originally, DOE wanted us to stick with Scope 1, but they slowly kind of adopted it to including Scope 2 in terms of how do you integrate various sources of power into the factory, okay? And so now we're looking at, those two aspects technologically. How do you integrate electric heating into a process, but also how do you integrate various energy sources, storage, all of that to basically power a factory. Okay, that's systems approach. And some of those things are also interlinked because you can grid synchronize processes and things like that, right? We have recently also expanded a bit. So we were all about electric power to heat, but we have now developed a concept around existing existing heat sources and integrating them into upgraded heat sources. So we call that a thermal transformer. You might have waste heat, you might have geothermal heat that is basically not useful for manufacturing. Now, can you transport it, store it, and boost it to the temperature that you want? Okay, that might involve, say, waste heat from a data center to produce steam. It might include integrating of small and medium reactors. So those kind of aspects have also been integrated into our institute. And finally, we're also looking at what type of training do we need to develop to deploy these in the field. So our mission kind of makes sense. It's basically accelerating the adoption of electric and hybrid heating technologies. But more than anything, we really want to develop an ecosystem where we bring in different players together that otherwise would not be working together. Okay, so how do we create that type of an ecosystem? So you'll often find that it's not just a problem for the manufacturer, it's also a problem for the utility. So how do we get projects together where the utility finds a gain, the manufacturer finds some win, and the technology provider as well, to develop a systems level project that there's a win-win, right? That's the kind of sweet spot that we want to be in, not just one-off projects with a single company. So we want to have our technologies such that, in the end of the day, they provide a cost-effective solution, either reducing operating costs, and also our solutions should be somewhat scalable, okay, to various types of sectors. So some of our priority areas and a little bit of our analysis that came out of our roadmap. So all the institutes are asked by their founding agencies to keep a roadmap that keeps being upgraded or updated every year. So we've done one as well. I think some of your Stratos and Mark and a lot of industries would have been involved in giving feedback to this. And essentially, this is kind of how we are looking at it in a very broad sense. So our scope is around what is there in that yellow box, right? So we're looking at electric heating, to some extent, to a smaller extent, cooling as well. And we are not looking at electricity for powering other parts than heating. So, electrochemistry or electro reduction, things like that are not part of our portfolio, but anywhere where we are heating, that's kind of where we play a role. And essentially, we look at it as if you have all kinds of sources of power. Some are intermittent, some are continuous. You also have all kinds of sources of heat. Some are continuous, some are intermittent. How do we combine all of that to power the factory that we need or supply the heat needed, right? And then, of course, the integration of that heat into our manufacturing processes. Electric heating has some unique advantages and challenges because you don't, in combustion heating, you can flood an entire chamber and you know what the temperature is. With electric heating, you don't always know that. It's interacting with your material. If you're microwaving, potatoes and carrots, probably end up at a different temperature. So you need to know and look at how the dielectric and all these properties, electromagnetic fields interact with the material. All of that has to be looked at, right? So, we are looking at also questions of that integration in terms of industrial flexibility. What would you want to do? Some industries want to have steady state operation. They want to have that power when they need that power, when it's not when the sun shines or the wind blows. So there's an extra cost then where you have to, basically give the base load, whether you do that with some type of a storage system or otherwise there's a cost to that. Other industries are interested in synchronizing their production with the power of the grid, the cost of electricity. So that's, the other way of that we are looking at it in terms of a systems problem. For example, there are breweries that operate boilers in tandem. You have an electric boiler and then you have a gas-fired boiler, and they're able to switch, almost on a day's notice based on electricity prices. So those kind of technologies, electric arc furnaces operate whenever there's cheapest possible way for that electricity to operate and what type of agreements they get with the power producer. So those are, systems level problems they're interested in. At UT Austin, they're also doing some interesting things in terms of grid synchronized distillation. Like, can you separate different things at different powers depending on the power usage and the power costs? So, originally when we stood up the institute, our goal was to a large extent decarbonization. Okay, so our projects all had a metrics that said cost of carbon abatement. You're going to abate carbon. Now, what's the cost of that? Can you bring that down? That's no longer a priority for the DOE or the US government at the moment. So we had to pivot. So our primary metric right now is efficiency. Okay, so the way we are looking at that is per unit energy spent, can you produce more products? Okay, so if you produce a certain, if you're spending a certain amount of kilojoules or watts, can you increase the amount of products that you're producing for that? Okay, that's our prime metric. Now, those of you who are thermodynamicists, see, there's a fallacy there. If you just operate near the second law, you don't produce anything, but you'll be very efficient, right? So you do have to maintain a certain productivity. So that's a caveat there, right? So, but that's our baseline for being energy efficient, okay? And it's not that difficult in a way. I mean, in a way, this has given us opportunities to work on some areas that we couldn't before. If you take things like, say, battery slurry drying, for example, it's not a big decarbonization problem, so we couldn't get into that. However, if you're replacing slurry drying with, say, laser technologies, you can produce much more. Even though the electricity price is higher for laser-based heating, your throughput is higher. So that's an economic interest, right? So we are able to get into areas that we couldn't get into before because of this as well. Okay. So that's the very basis of what we are thinking about. Now, we have to think about some other things here. There are some non-energy challenges and opportunities as well. It's not always a one-to-one replacement. If you take my own area, say iron and steel, one big area of energy intensity is rolling of steel. And there are opportunities. You would be way more energy efficient if you could say induction heat a coil, okay? Because you're just heating what you're heating and nothing else. You would almost reach the thermodynamic limit. But the problem is that you don't know whether you're getting that same quality, okay? So we have to make sure that the product quality is the same. In some cases, it could even be better, because you can heat what you want to heat at the temperature you want to heat. So you might be able to create microstructures that you couldn't before. Okay? As an example for steel making, you conventionally heat it in a reheat furnace in a combustion atmosphere. You end up with a lot of scaling. Okay? You end up with a lot of oxide scale. And that also actually limits the amount of recycling you can do because copper contains, steel scrap contains copper. And when you oxidize the surface, that copper prevents you from making high-grade products. It creates cracks on the surface. That's probably the biggest problem for scrap-based electric arc furnace production. Now, with electric heating, you could potentially operate in an entirely inert environment. Okay? In an inert environment, where you don't create any scale, and you could get a better product out of it, right? Even downscale, if you're looking at annealing, you could create all kinds of quench structures that you couldn't before that would actually add to your product value, so to say. So those are kind of opportunities that we are thinking about. Now, in a systems level integration, if you go one step higher, you can't just limit it to that one process. It's not a one-to-one replacement. You have to think about stuff like fate of the fuel gas, heat integration, what happens to all of these things, the available power. Somebody mentioned very accurately that most plants have already done their pinch analysis, right? So whatever heats and sinks are going on, you're using it somewhere else. So by electrifying one part and not using the rest of it, you might have to provide more power. I mean, any of you who may have an electric car and you're trying to use the air conditioning or heating, doesn't last as much as a gas-powered car, right? It's pretty optimized. So you have to look at it from that point of view. On the other hand, you might get gains, such as, there might be less moving parts, process flexibility, all that stuff that has to be replaced. Okay. Some interesting questions have come out of this that we didn't think about originally, right? So one of the limitations from industries to adopt technologies is sometimes not even the cost, but it's the downtime. Okay, it takes a certain amount of downtime for them to replace their systems and the loss of productivity there. Okay, and one thing they've asked for is, can you create a model for us depending on what the facility is that would expect the downtime to replace? If you take a simple thing like a I don't know, a boiler for a beer factory, beer producer, distillery, how long would it take downtown to replace this? And that means all the logistics that goes with it, because sometimes these parts come from Denmark, somewhere in Sweden or Norway, and all that repair and stuff, how long do we have to take a risk of not operating, right? Or do we wait till something's broken anyway? So those kind of questions have come up as interesting problems for us. Please, if you have any questions at any point, let me know. So as a summary, any project that we do, primarily there's an energy impact, and then there's a non-energy impact as well, okay? We also had a non-energy impact of emissions, but that's another word I can't use anymore. So emissions is not in my vocabulary. So I'm not allowed to say emissions, but in the end of the day, you can imagine that you also get less particulate emissions, right? Whether we want it or not. Workforce challenges. So I don't look that way, but I'm actually Swedish. So this is in the very, very north of Sweden, okay? If you think about where you would produce and have the next industrial revolution, it would be there. You have over 70 terawatt hours of electric power. You have almost all the natural resources you need in terms of mining and ore. Problem is that if you've ever been there, there's more reindeers than people. There's nobody to work there. So the workforce is a problem, right? So we have created our educational institutions around where there was coal, water-based, stuff like that. But those are not necessarily where industry is growing, right? My own interest is iron and steel. And if you look at where all the major iron and steel educational hubs are, they're all in the Northeast. But guess where it's growing faster? It's actually Texas in the South. Okay, you don't have a single steel hub anywhere around these areas. So there's a redistribution, and people from the North don't necessarily want to move and all that stuff, right? So there's a workforce challenge. Like, we can develop a perfect place to build a factory, but it doesn't mean that we have a workforce over there, okay? I was in the state of Oklahoma a few weeks back, and one of their questions was, we have so much abundance of natural gas, why don't we become Texas in terms of manufacturing hub? But one of the limitations is they don't have the educational institutions like you guys have. So training people and the workforce is a limitation for industrial development. This is just a graph that I put together for AIST, the American Iron and Steel, that basically shows where the educational programs are, all in the Northeast, but the growth of industry is along the South and Texas. Right? There's a mismatch there. That's a case I would make for the government, that they need to redistribute educational programs more to Texas and the South. Yeah. So we do have a manufacturing education program within EPIXC as well, but it's kind of partnered with the other 18 or so manufacturing institutes. And we develop skills from the very, very base level all the way to PhD in all kinds of ways, right? I wouldn't say it's that well developed yet. So this requires some work, right? Because a lot of these institutes are put together by academics and scientists who don't necessarily know how to train apprentice programs and pre-apprentice programs and things like that, which is really what we need.
Any thought about dual vocational programs, Sridhar, there, or emulating the Germans, because I know you're familiar with them?
We have tried some of that. One challenge, I guess, is in Germany, and then we've talked that within the institute director. So in Germany, there's a culture for industry to have a pride in doing this. So, you can call up Thyssen or Salzgitter and say, hey, we're doing this, and then they'll feel shamed and they'll support it. In the US, it's so difficult to get industry to actually buy in and actually commit cash to programs like that. We are trying that, but we've tried with Motiva, we've tried with all kinds of industries. But for them to actually join a program like this and pay for education is a challenge.
At least 3 US presidents spoke about the value of dual vocational programs, starting from the Obama administration.
Yeah.
And we still haven't moved forward. That's the reason I'm asking the question.
Yeah.
You see it because both sides of the Atlantic.
Yeah. It's been a challenge to get commitment for industry for that. Now, I don't know what it is in Germany that makes it work. Maybe traditionally they've just been.
But they start tracking students from very early on.
Yeah.
Which would never fly in this country.
Yeah, that's true too. You make your decision at an early enough stage, right?
And even if you go there, you don't have the stigma of not being an academic path because they can bring you back, right? You go back on DBB, I think is the acronym of the organization. I used to work with them, but you can go back, reintegrate in a PhD program later down the road, things that we don't have here.
Yeah.
But when you look at it, everybody talks about dual vocational programs being a choke point for us in the US.
Yeah.
And I think people like you, the systems thinking, true leaders like you can make a difference there.
Yeah, I think this is an area that we could make a difference, and maybe working with the USA manufacturing institutes, because I think all of them face that problem, not just EPIXC, but all the institutes, right? So, and we need some leadership in this. So, you guys being a core member in EPIXC, it would be great to get some help in this area. So some key findings from our roadmap, right? This is an interesting graph that we like to show, and Mark and Stratos have seen it before, but it just shows the cumulative energy at different heat duties at different temperatures, right? It's kind of tempting to think about something cool as melting of iron and steel over 1700 degrees. That's where a lot of heat is going to be produced. That's where we should be working on. But it's actually not. I mean, if you look at these low temperature regimes, there's so many industries that use those temperature limits that you could impact a lot of industries if you're able to target this area here, right? Versus just a few plants over there. Also, there's a lot more modularity over here that the risk is less. You're not looking at an enormous smelting plant, but you're looking at maybe a neighborhood bakery or something like that, right? So we do address all these different areas, but our roadmap kind of suggested that we might want to focus on these areas here where we might be able to make the biggest impact. I'll show this graph later, so I'll come back to that. So we're also thinking about, what might be co-benefits of electric heating, and mentioned some of this before. But you can control the heating where you want, how much you want to heat much better. And you might have a lower cost of capital parts, and you might be able to differentiate your product, as I kind of mentioned earlier. So our goal is kind of to look at, there's going to be a higher price, especially in the US, it's very difficult because of the natural gas prices, right? I was over in Denmark a couple of years ago for a US government trip. Denmark's industry is all electrified, so is almost Holland's. And we were trying to understand how did they make it work economically, and could any of that be replicated in the US? So first they will tell you all this stuff, that it's our commitment, moral commitment, ESG, all that stuff. But if you keep asking them, that's not at all it. It's because EU has very strict rules that they have to decarbonize. So they don't have rules, so they don't have a choice. So they have, a 10-year rate of return for the technologies. Second of all is Ukraine. They don't have the cheap natural gas they used to have. Third of all is, they have this enormous battery from Norway and Sweden of hydroelectric power. And then they can base that and supplement that with their own wind and solar to basically be carbon neutral. There's an economic case. We don't have that in the US, and the US is so broad, so there's differentiation wherever you go in the US. There's diversity in electricity sources. So we have to think about it as a regional problem, right? If you're Pacific Northwest, you might have access to a lot of hydroelectric, but the rest of the country is dependent on, to some extent, intermittence. And to beat natural gas is hard. So in terms of our roadmap, one of the things we looked at is if we look at all the different things, not all the different things, but many of the different things that our stakeholders are doing just in terms of processing, and then looked at the average heat duty per kilogram product, then what's the areas that would make a biggest impact? And we found that the major source of energy use is just making steam for all kinds of ways, whatever you use steam for. It's not a very, that much of a romantic problem to look at compared to, say, iron and steel. But because of the vaporization energy and the latent heat of vaporization, steam is the biggest source of energy usage. Okay? And that's been a focus for us. Steam is also, to some degree, a lower hanging fruit for us because there is lower amount of risk. Like you produce steam, you move it somewhere else, but the way it's used in your manufacturing process, it doesn't care how that steam was made, right? Whether you heated it with natural gas or electricity, it's still the same steam, owing to some water quality issues. But so it's a lower risk. Whereas, if you're thinking about integrating a plasma furnace for heating or something like that, there's a lot more risk because you may cause all kinds of things in the manufacturing step itself. So steam usage seems to be a lower hanging fruit for us to work on. Now we looked at all these different heat duties. This is how much heat it takes to make something. And we tried to match that with what are the different heating technologies you have and what can they achieve today, okay? And there's a limitation of what is reported in literature. For example, heat pumps, electron beam melting, whatever you take, there's some limitation that allows them only to go to a certain degree. What that limitation is interesting. And while we can't go to that granularity, I think it's an interesting question because it may have to do with the power systems, the power electronics that can power a plasma unit. It might have to do with the alloys that work as a heat exchanger. But there are all kinds of reasons why these are limited to certain power. Okay? One very interesting question that came up in one of our workshops a couple of weeks ago in Austin was one hesitation that companies have to adopt these technologies is the supply chain. Okay, that these supply chains don't always exist in the US. They come from abroad, and we don't even have the automation engineers, the repair engineers to repair a lot of these technologies that come from Danieli in Italy or from Japan, places like that, right? So that's a hesitation they have. Even heat pumps, a lot of the heat pumps are created by Danfoss, produced by Danfoss in Denmark, and we don't have the repair engineers put those in. So that's a hesitation that industry has from adopting them, right? This is an area that we think would be interesting to get into to almost make a toxicology, some kind of a metrology in terms of taxonometry, in terms of you break these things down to components, materials, parts, where does the pinch point exist, and identifying those just to inform the government that these are problems, right? It's something that your institute might be able to help us with as well for looking at. We did something similar with wind turbines a while back, but when we broke wind turbines down to parts, to raw materials, and then try to make a chain of where are the pinch points. And something like that with these heating technologies would be really cool to do.
That's something you can definitely add value there. You're talking about supply chain mapping.
Yeah.
Understanding scrubbing, as we saw, low tier dependencies, choke points, and all the great stuff.
Yeah,
We'll
and
have to-
even maintenance, if you have to fly somebody in from Holland or Denmark versus creating those kind of things, right?
Yeah.
It's something that we're not looking at now, but I think we should be looking at it, and there might be other opportunities we can go after. Right? Yeah, so that came up, and as a prime reason why industry is not adopting them. Many steel industries, for example, they demand that you have 2 or 3 alternative suppliers for a technology before they adopt it. It doesn't matter if the technology works or not. So, and we don't always count for that, right? This is a graph that, or a chart that my colleague Mark Michael Baldea from UT Austin put together. And you can see that, this is where we got information from all our stakeholders, but there's a lot of white area here that we don't have information about. It doesn't mean that it doesn't exist, but there's stuff that we have to complete in terms of other technologies that can actually achieve certain things that just hasn't been reported yet. There's no, physical law or thermodynamic law that says that they can't do it. It's just not been explored yet. Whether those areas can be looked at in terms of technologies.
In our legacy industries, it's still looking for alternative?
Absolutely. So for reasons that may not be obvious, for example, the steel industry in the US, well, there's also an interesting problem in England. I was contacted by Wales, because they're trying to put in an electric arc furnace in a hotel, and somebody asked, can we convert, can we buy an electric arc furnace? Sure, you can buy an electric arc furnace, but you need the power to power it, right? That's the problem. Everybody can buy an electric arc furnace. So they're trying to look at, Swansea Bay and all this stuff in terms of what they can do to power that system. I have my doubts, but we'll see. But in the US, we operate around 110 or so electric arc furnaces all around the country. And the electric arc furnaces are the mini mills, which they're called. They're in such a scale that it doesn't make sense to build a entire power plant like you can do in an integrated plant, which are actually energy producers, right? There's no technology really to recover the heat. So I would say the biggest interesting challenge for the electric arc furnaces are if you can capture the waste heat, which is emitted around 1800, 1700 degrees centigrade, and it's carbon monoxide that's post-combusted to carbon dioxide. And that heat is not captured right now. If you can capture that heat, then the plant could be 70% self-reliant. And they're interested in that because they're not able to get the power they need to expand. For example, in Arizona, CMC Steel, which is one of the most modern steel plants you'll ever visit. If you have a chance, come there. There's almost no workers. Everything is optimized. Everything is electrified. But they cannot expand their plant because of competition with data centers and Intel, or not Intel, not TSMC or whatever it is, right? So they're looking at basically self-reliance and distributed energy systems to be able to power themselves. So the steel industry is absolutely interested in that from a power management point of view.
That's a huge point that you raised, right, for us, because we're looking at BTM technology for data centers. But what you say now is the steel manufacturers, producers face the problem themselves so they can look at their own BTM technologies, grids, right? Amazing.
Yeah. And the interesting problem with steel, for example, is power and heat. They need direct heat, but they also need power. So the combination of solutions might be different as well, right? There's a company called Vega, I think, that looks at sort of localized geothermal energy. And they claim that they can do cost-effective geothermal energy within 1 or 2 years for single plants. I don't know how it works, but those kind of technologies might be interesting to look at as well. It's still too expensive, but on paper, small and medium reactors potentially could give you power and heat, right? No, absolutely. So the industries are really interested in this because their main worry is the availability of power. I mean, and another, from a decarbonization point of view, an interesting question comes up. If you do have power from the grid, where should that power be used for most efficiently, right? Even in Sweden, where you have these green steel projects, there's a discussion, why should you make steel when you can just export that electricity to Balticum or Finland? One of those steel plants consume as much power as like 3/4 of Finland. So if you really were out to decarbonize, you would first decarbonize the grid and then look at those things, right? So that becomes an issue, and then the steel plants are forced to start looking at their own power supply as well. So some of our ongoing research, I just want to highlight. Let me know how much time do I have?
Yep. 5 minutes.
Okay, so I'll finish quickly. So we've been trying to find cases where there's economic reason to do this, right? Previously, we could do it for the sake of decarbonization. We cannot anymore. So we have to show industrial economic viability first and foremost. This is a project at UT Austin. This is their pilot plant. So essentially, we are looking at distillation with e-boilers in tandem with combustion boilers to see if we can produce different products at different power systems. Basically synchronize the production with the price of the electricity. This is basically the system that they're building up at the UT Austin. If you ever go there, please have a look at it. It's pretty cool. Another project is this is being built at ASU. So it's basically a calcination reactor, an electric calciner. The value there is that with electric heating, you can have more uniform heating. So you can use more flexible set of feedstock. Okay, so you can use clays and stuff like that. So that gives you a feedstock flexibility that then gives you a product, an overall cost effectiveness. Just a kiln. This is a project in Tennessee where it's a collaboration between TVA, CMC Steel, EPRI, and Siemens, where we are looking at electrifying the reheating process and preheating of reactors and coming up with the economic system to make sense of that, right? They have a decarbonization goal, so that's part of their incentive as well, but whether we can present that to DOE or not is different. We are building a pilot scale rolling mill that's actually heated by plasma heating and induction heating. And this would really be the first one of its kind. Few minutes left. In the end of the day, I'm a scientist, so I have to show something geeky, some research stuff as well. This is actually not funded through EPIXC, it's funded through basic energy sciences. One of the biggest problems that the steel industry faces is, you've probably seen a lot of literature around H2 DRI and stuff. It cannot be scaled, okay? The reason that it cannot be scaled is that DRI relies on very high-grade iron ore, okay? You produce an iron ore that has a lot of gangue in it. That cannot be cost-effectively produced in electric arc furnaces, okay? So if you wanted to really look at an alternative way of making iron and steel, it doesn't work. The only way to do it is to develop a smelting technology where you separate the iron product from the gangue. Okay, so ultimately, if you look at it, the traditional DRI produces iron, but it has a lot of gangue inside it that cannot be used in the electric arc furnace. What you would want to do is produce a product where the iron is separated from the gangue. Okay. Now, one potential way of doing that is plasma smelting. Okay? Plasma smelting has two advantages. Number one, the radicals that you get, they have a higher kinetic potential for reduction. So you could operate at lower, much more higher efficiency, but also it provides you the power, the amount of energy to basically melt everything. And the molten oxides, which are like lava, are immiscible with the iron, right? So that's a technology that we're looking at. It's not funded through EPIXC, but by DOE's Basic Energy Sciences. And UT Austin is a part of this as well. They're doing all the plasma modeling. And this is just a sample that we produced out of that process. Some advantages of plasma smelting is that the free energy is actually, it becomes exothermic as opposed to endothermic. So the energy efficiency is there. you can make use of these particles. And plasma, if you look at the other side, has the potential of scaling up to the amount of power that you want. Okay? There are some power electronics limitations, but plasma itself can do it. This is just examples of the reduction that we've done, and we've shown that you can improve the kinetics with plasma. We also have ways of actually imaging how the metal precipitates at high enough temperatures. This is just real-time imaging of how iron crystals are produced out of molten oxides. And it's just some cool images of high temperature microscopy that I kind of have to show. Anyway, so plasma modeling of the reactor is done in Austin, and they're connecting with the metallurgical model. So we're looking at, since it's a basic energy science stuff, we have to get into all of that. I'll summarize there. So, basically EPIXC is an industrial consortium. It's for industry, run by industry, and we are trying to take advantage of advanced electric heating for benefit of industry. And I would say that at the moment, chemicals and metals are our main core sectors. Some underdeveloped sectors that we are looking to develop is food and beverage. We don't have enough of food beverage companies, but that's one thing that we are trying to move into. And we're open for any US-based organization to join. Thanks.
Thank you.